Hello, I'm Heesoo from NAVER Corporation. I will present submission of Team NAVER Clova to the third DIHARD challenge. Our system is built on top of the common stepwise pipeline of speaker diarization. This system is composed of three components: an endpoint detection module, which is only for track 2, a speaker embedding extractor, and a clustering method. We use this system as the baseline. Our submission to the DIHARD 3 challenge include two main contributions of the existing baseline. First, we built an overlapped speech detection system and put it between the EPD and speaker embedding extraction modules. Second, we designed a feature enhancement technique for speaker diarization. This technique includes session-level dimensionality reduction and attention-based aggregation. The feature enhancement technique is applied after extracting embedding vectors. Let's start with the overlapped speech detection system. This system finds onset and offset of segments that contain more than one speaker's speech. Our overlapped speech detection system has three features. First, we train the DNN as a three-class classifier, namely non-speech, single-speaker speech, and overlapped speech. In the test phase, we use the output layers node that indicates overlapped speech. Second, we augmented the training dataset by adding another speaker segment in the middle of a single speaker segment. This augmentation was performed and increased the ratio of the overlapped speech. Last, we use a CRNN architecture instead of the existing system based on RNN. For the DIHARD submission, we used a school-level ensemble of three model variants: 2D CRNN model with SE, 2D CRNN model without SE, and 1D CRNN model without SE. To incorporate the development overlapped speech detection model, we modified our process pipeline to minimize clustering error caused by overlapped speech. We aim to minimize the effect of overlapped speech in the clustering phase. To do so, we extract speaker embedding only from single speaker segments and perform the first speaker clustering. Then for each overlapped segment, we predict two labels based on centroids of clusters. For example, we find top two centroids with high similarity and assign the corresponding labels for each embedding of overlapped speech. Our second main contribution is adding the feature enhancement module to the process pipeline. Feature enhancement is common in machine learning field. However, if we were right, it has been explored for speaker diarization. Compared to speaker identification or verification, the speaker diarization task requires the less number of speakers at once. The speaker diarization task requires discriminative power between only 5 or 6 speakers at most scenarios, while the common speaker verification task requires discriminative power over the thousands of speakers. Thus, we assume that speaker embedding should be projected to a new representation space that shows discrimination of small number of within-session speakers. To achieve this goal, we first reduce the dimensionality of speaker embedding using an autoencoder that is trained for each session. The autoencoder is composed of two layers, one for the encoder and the other for the decoder. For the encoder layer, we apply max feature map activation. Using the trained autoencoder, the 256 dimensional embedding vectors are replaced with 20 dimensional enhanced representation, or code. Note that in dimensionality reduction, the autoencoder is designed to run reconstruction of only one session after random initialization. And detailed architecture of the autoencoder is as follows. The input to the autoencoder is 256 dimensional embedding vector. The output of the first hidden layer is a 40-dimensional representation. The representation is compressed into 20-dimensional code by element-wise max operation. To build an output of the autoencoder, 256-dimensional vector is reconstructed from this code. And this whole architecture is trained to minimize MSE error between the input and the output. The role of MFM operation implemented by element-wise max operation is to extract and effectively compress information of speakers included in one session. Finally, the code from the autoencoder replaced the existing embedding vector after training the autoencoder. Then we aggregate embedding vector using a self-attention mechanism. We have prepared a short PyTorch code to introduce this concept. We calculate attention map for each embedding using support map function and iteratively update embeddings based on these maps. There are two hyperparameters in this technique. The first one is number of repetition, and the other one is temperature value before support max function. We fixed these two values as 5 and 15 respectively. We expected that the attention-based aggregation technique would make speaker embedding robust to outliers and refine the affinity matrix. These two figures show the effect of attention-based aggregation technique on the affinity matrices. We could find that most of noises in the affinity matrix were removed by this technique. Such an effect would be useful for most of clustering methods which are performed using the affinity matrix. Now let's move on to experiments. First, the overlap speech detection system. We used AMI corpus, box converse, and DIHARD 1 and 2 development set to train the model. The submitted model were tuned using DIHARD 3 development set. We tuned the threshold of each model to get a precision of 0.8. This graph showed the result of our three individual models and their score level ensemble. The ensemble model demonstrates recall of 0.55 on the DIHARD 3 development set. In order to build the embedding extractor, the public resonance structure was utilized along with several modifications. We used both of Boxlet 1 and 2 development set to train the model. The 64-dimensional features were used as frame-level feature. The number of filters in the first convolutional layer was configured to 64. After the last convolutional operation, average pooling was performed for aggregation. The dimension of embedding was set to 256 dimensions. For the spectral clustering, we calculate affinity matrix using cosine similarity and do not apply any additional refinement process on this matrix. To determine the number of clusters, eigenvalues greater than 20 are counted. We perform k-mean clustering on the spectral embedding to estimate the final cluster labels. This graph shows the performances of various diarization systems in DER. First, we found that The proposed picture enhancement technique increased the performance with a very large margin compared to the baseline. An additional performance improvement was achieved using the output of the overlapped speech detection model, and we also found that the proposed overlapped speech detection model and picture enhancement technique can be effectively applied to other clustering methods, such as AHC. Finally, we submitted the system that achieved 40.97% DER on the development set as the primary system. These results are from the leaderboard of track 1. Our primary system achieved 50.40% DER on core set, while achieved 13.95% DER on full set, and ranked third and fifth place on core and full set respectively. This is summary of our presentation. There are two contributions on stepwise pipeline. The first one is overlapped speech detection using an ensemble of CRNN-based models. The other one is a series of feature enhancement for speaker diarization, dimensionality reduction, and attention-based aggregation. Our system achieved 15.40% DER on core evaluation set and 13.95% DER on full set. Thank you for your attention.